Hello guys, welcome to my YouTube channel. Today we will be talking about iron metabolism, that how iron is absorbed from our GIT and how it is transported and how it is utilized. Okay, so let's start. Okay, so this is your duodenum, right? And this is stomach and this is your duodenum. Now you should know that the iron is absorbed from the duodenum. Okay, now I am here showing you one enterocyte of duodenum largely here. Okay, so suppose this is that cell and this is the apical side and this is the basolateral side. And okay, I should find some red pen. Just a minute. Okay, so this is the enterocyte and this is blood vessels, and this is bone marrow. And this is liver, and here I'm showing you the macrophage. Right, now what happens, basically iron can be absorbed in only one form, that is Fe2 plus, right, from GIT to the cell. But here what happens, okay, I said only one state, that is Fe2 plus. Okay, now you should know one thing, that the iron we take from our food, it can be in two form. One is known as heme form, right, which comes from the animal source. Another one, that is the inorganic form, which comes from the vegetable source. You should know that the heme form is more absorbed and the inorganic form is poorly absorbed in our GIT, right? So in inorganic form it is basically in Fe3 plus state, and heme form, you know, that is Fe2 plus. Heme form, that means it you can find it like in meat, or meat have myoglobin, so from there we can have it. So I'm showing you by different colors. So this heme iron is come here like this, and inorganic is like that. Okay, so in the enterocyte there is one channel, which is one transporter, which is heme iron transporter. Okay, so it basically transforms the heme iron into the enterocyte. Okay, and the inorganic form, that is Fe3 plus, it can be absorbed like that. It must be converted into Fe2 plus before absorption. So that is why here is one enzyme is there that is known as ferrous reductase. Okay, in the basal in the apical side of the enterocyte, the enzyme is also known as cytochrome B. So this enzyme causing the Fe3 plus convert to Fe2 plus, and by here another enzyme, another transporter known as divalent metal transporter 1. It helps in transport of the Fe2 plus from the duodenals, from the duodenum into the enterocyte. Okay, so finally it comes here, Fe2 plus. Now this is the enterocyte, and you must know here that this cell forms a lot of protein named apoferritin. Okay, apoferritin, it forms a lot of apoferritin. This apoferritin binds with Fe2 plus and forms ferritin. Okay, now you should know one thing, that only 10 to 20% of the iron of the only 10 to 20% iron is absorbed from our GIT, from the taken food, only 10 to 20%, because of one reason. Now look here, that Fe2 plus, this Fe2 plus binds with apoferritin, which is produced by this enterocyte, and this ferritin is like this. Okay, and some amount of Fe2 plus is free here, right? So what happens to them? There is another channel here is known as ferroportin. That ferroportin, okay, name as ferroportin. Now this ferroportin helps to transport this Fe2 plus from enterocyte to the blood. Okay, so it comes here, Fe2 plus, but you must have remember that Fe2 plus state, in Fe2 plus state the iron cannot be transported. So that is why here another enzyme helps in reduction of this, oxidation of this Fe2 plus to Fe3 plus. Okay, that is oxidase, is known as hephaestin. Now this Fe3 plus, obviously this free Fe3 plus cannot be transported, like, because it is a polar substance. That's why it causes damage. It can cause the DNA damage or the tissue damage wherever it goes. So liver produces here transferrin. Okay, now this transferrin is like this. One transferrin can bind to 2Fe3 plus, and Fe3 plus is bounded like this, and this transferrin can transport this Fe3 plus in the blood. Now after binding to Fe3 plus, it can go three places mainly. One is bone marrow, where it is needed for the RBC production. Okay, another one, that is the liver, where, okay, 1 minute, and there is the liver where it is stored mainly. and it may be stored in the macrophage. I mean, you should know that the macrophage is the ultimate place where the iron is stored in our body. That macrophage may be found in the bone marrow, liver, spleen, anywhere. So what happens here? So you know that bone marrow, in the bone marrow cell, I take any particular cell, okay, like the erythroblast series cells, which needs that iron. So they show one particular receptor for transferrin, known as transferrin receptor. Now this transferrin binds to the transferrin receptor, and after then here the clathrin molecules are attached in the inside part of this cell membrane, and then finally it is endocytosed. After endocytosed, lysosome comes and causes ultimately release of that iron. Okay, this iron then go to the mitochondria. Now to formation the heme part of the hemoglobin, for the formation of the heme part of the hemoglobin. Okay, so 1 minute. So you should know here that how it is formed, that is, if this is the mitochondria, it is this is the mitochondria. Okay, so here the heme part is I mean the iron part is come, and here within the mitochondria and one enzyme, one group, that is succinyl CoA and glycine. Okay, succinyl CoA plus glycine formation of amino levulinic acid. Then two molecule of ALA form one pyrrole group, and four pyrrole group ultimately forms the protoporphyrin. Okay, this protoporphyrin again goes within the mitochondria, and after binding with this iron they form the heme part. And within the cell, okay, mRNA formation, and after mRNA formation there is a globin part formation, and heme plus globin equal to hemoglobin. Okay, so this ultimately leads to formation of hemoglobin, right? Now now what is now this part, that is the transferrin, this transferrin and the transferrin receptor, which is previously endocytosed here, they are after taking the iron, they are throw out to the blood. Okay, so transferrin again comes in the blood, so they can bring more amount of iron, and some transferrin receptors are also thrown to the blood sometimes. Okay, so this is the ultimate transportation and utilization of it. Now the excess iron is stored in our body, in the liver, within the macrophage. Okay, so so ultimately the bone marrow forms RBC. Okay, they ultimately form RBC. This RBC has 120 days lifespan. After 120 days they go to the spleen, and finally the RBC was trapped within the spleen. Because why? Because you know the RBC has no nucleus, so it cannot form its protein, which are needed for its membrane uh, I mean for the membrane elasticity, right? So that is needed. So after 120 days it becomes very much brittle, and it cannot squeeze correctly. So in the small vessels of the spleen they get uh, stacked there, and in the spleen macrophages come, and this macrophage causes the phagocytosis of the RBC. So within the macrophage, what happens? The RBC finally phagocytosed and its different parts uh, separated, like hemoglobin is separated, the heme part is separated, the globin part is separated. This globin ultimately forms amino acid, which is again used, and the heme part, you know what happens to the heme part, that is it ultimately forms the biliverdin and then the bilirubin and finally comes through the bile, and you know that part. Okay, so that is the heme part. Okay, so here again the Fe part, the iron part is separated from the heme. Okay, so this iron ultimately binds with the apoferritin. What? Just a minute. So this ferritin is ultimately, the iron part is ultimately bind with ferritin. Okay, apoferritin, and then formation of ferritin. Then this ferritin, what happens here, that a lot of ferritin, sometimes a lot of ferritin is formed within the macrophage, and this can lead to formation of hemosiderin. So what is the difference between hemosiderin and ferritin? Very simple. The ferritin is monomer, and if the ferritin is so much, then it becomes a lot of ferritin comes and stuck together, and there is formation of hemosiderin. You should know this. Now one thing you should know about hemosiderin, that sometimes we call stainable iron. What is stainable iron? Stainable iron means, this is hemosiderin. Okay, stainable iron means we can stain the hemosiderin with the stained Prussian blue, and that is absent, that is negative in case of iron deficiency anemia, because in iron deficiency anemia the iron stores of our body gets depleted. So that is why this test becomes negative. So this is the ultimate fate, you can say. Anything I'm missing here? Okay, so yes, one thing you should know, that this ferritin part, this ferritin ultimately comes to the blood. Okay, this ferritin, that is apoferritin plus iron, ultimately comes to the blood, and this is proportional. The blood or serum ferritin level is proportional to the iron stores of our body. If this get depleted, the serum ferritin, that means our iron store of our body is also gets depleted. So it is very much important here. Okay, and when it is very much less, then ultimately hemosiderin becomes break into the ferritin, and it comes in the blood, because the iron, in case of iron deficiency anemia, sometimes there is problem in iron absorption, sometimes there is problem in mainly iron absorption problem there. So in that case, the iron stores of our body is used for the production of RBC. So in that case, this hemosiderins breaks into the ferritin, and this ferritin comes in the blood, and they are ultimately used. Okay, so this much you should know, and this is the very first part. Okay, so another thing I missed here, that is hepcidin. Hepcidin is a molecule that is produced by the liver. Okay, that is produced by the liver. This is the master regulator of the iron metabolism. Why? Just look here. This ferritin is produced by the liver, so this is like a molecule which causes binding to this ferroportin. Okay, so if it binds to the ferroportin, and ultimately degradation of the ferroportin occurs, so that is why there is a problem in absorption of ferrous. Okay, and it also block the transportation of ferritin from macrophage to the blood, I mean from different stores of the blood to the blood. Okay, so ultimately the serum ferritin level goes down, so it helps in uh, we can say iron toxicity. Okay, it is protective there. I mean, if there is increase in hepcidin, there is decrease in iron ultimately. Okay, should know that. And one thing I also missed, that is about the transferrin. You know, the transferrin can bind to 2Fe3 plus. Okay, so normally what happens, there is a term that is known as transferrin saturation. Okay, if there is 3 molecules of transferrin, okay, only one of them is bound to the Fe molecule, because and rest 2/3 is not bound to the iron. That means the normal saturation of the transferrin is 33%. Now I'm coming to the iron deficiency anemia. In iron deficiency, okay, so in iron deficiency anemia, what are the causes? Causes can be, here you can think that there is a decrease in absorption. Okay, so one thing, that is decrease in absorption. There can be increase in demand, right? There can be decrease intake, I mean dietary cause. And the fourth reason is chronic blood loss. Okay, now you should know, or you already may know, that sometimes in chronic blood loss, in case of female, in their reproductive age, they lost around 20 to 30 ml of blood during menstrual period. Okay, and sometimes gastric carcinoma or peptic ulcer, they also can cause huge blood loss. That is why anemia may be there. But here one thing that is worth to one thing you should know, that in case of adult men and postmenopausal women, if there is iron deficiency anemia, okay, if there is iron deficiency anemia, so you must do endoscopy, because maximum time it is due to peptic ulcer or gastric carcinoma related disease, because these are the only thing that I mean, this is the very much common there. Okay, so